Hi, Assalamualaikum to everyone. Today our group will present chapter 4, Newton's Law of Motions. Our group has 5 members, which is Zahira binti Samsudin, Nur Zahira binti Aznawi, Nur Akila Fakira binti Ayub, Faraiza binti Muhammad Taib, and me myself, Nur Ashna Sira binti Baharudin.
First of all, I will present to you about force. Force is the measure of interaction between two objects which are pull or push. It has vector quantity and has magnitude and direction, and it may be a contact force or a field force. Contact force results from physical contact between two objects, and field force act between disconnected objects and also called action at a distance. As you guys can see, the right of our slide have a few examples of field force and contact force. In this chapter, there are 4 types of force. First is gravitational force, second is friction force, and third is tension force, and the last one is normal force. Next, I will present to you about unit of force. The formula of force is F net equal to summation of F equal to ma. M is mass times with acceleration. SI unit of force is Newton, and 1 Newton equal to 1 kg meter per second squared. In US customary unit of force is a pound, which is IB, and 1 Newton equal to 0.225 IB. Weight also measures in IB. Next, I will explain to you about gravitational force. Gravitational force is a vector, and it expressed by Newton's law of universal of gravitation. The formula of gravitational force equal to G multiplied with m over r squared. The capital letter of G is gravitational constant. The capital letter of mass of m is mass of the earth, and the small letter of m is mass of an object, and the capital letter r is radius of the earth. And the direction of gravitational force is always pointing downward. Next is weight. Weight of the object is the magnitude of the gravitational force acting on an object of mass near the Earth's surface, and the formula of weight equal to mg. M is mass and multiplied with g is gravity, and g can also be formed from the law of universal gravitation. As you guys can see in the slide, the formula of gravitational force equal to G times with mm over r squared, and if we derive the formula, we can get the value of gravity, which is 9.8 meter per second squared, and weight also has a unit of Newton. The next one is tension force. In tension force, a taut rope exerts forces on whatever holds its end. For example, in the slide, you guys can see there are 2 people pull a rope. The tension force will exert when 2 people pull a rope. The direction of tension force is always along the cord, which are rope, cable, in-rope cable, string, and others, and away from the object. The magnitude of the tension force is depend on the situation, because there are many situations that may have a tension force. The last one is normal force. Normal force is a force from a solid surface which keeps object from falling through. The direction of normal force is always perpendicular to the surface, and the magnitude of the normal force is depend on the situation. There is an example in the slide. Normal force is always acting perpendicular, as you guys can see in the slide. And if you want to get the value of normal force, you can use the formula of force, which is force equal to ma. And if you derive the formula, you can get the normal force equal to mg, because there is only gravitational force and normal force in the situation.
Okay, next is about the Newton law of motion. There are three types of Newton law of motion. First is Newton first law, second is Newton second law, and third is Newton third law. Newton first law. Definition. Newton first law states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and same direction unless upon by an unbalanced force. Unbalanced force can change the velocity of the object, speed up or slow down the object in motion, and can change the direction of the object, but depend the force that you apply. When a body either at rest or moving with the constant velocity in a straight line with the constant speed, we say that the object is in equilibrium. Okay, formula for the Newton first law. Total force is equal to 0. As you can see in the diagram, there are two cases for force imbalance. Okay, first, an object may be at rest, or second, an object will be in motion at non-zero constant velocity in a particular direction. Okay, in the first case, the object will continue to remain at rest, and in the second, the object will continue to stay in motion at the same velocity and the same direction. And don't forget this, two cases will true if only forces are balanced. Okay, to understand clearly about the concept of Newton's first law, let's see this example. Okay, at the left side, the ball is at rest, and when the unbalanced force acting on this ball will move. And same goes for the ball at the right side. The ball is at the constant speed, so when the unbalanced force acting on this ball, it will make the ball accelerate and change its direction. And next is about the Newton's second law. Okay, definition. Newton's second law states that the acceleration of object is directly proportional to the force acting on it and inversely proportional to the mass. Okay, formula for the Newton's second law is a total force is equal to the ma. One example that we can see for the Newton's second law is when we threw the ball downward with the force 40 Newton. Okay, this ball will experience acceleration in which acceleration of the ball is equal to the gravitational force. Okay, next is about the relationship between the force and mass. Force is directly proportional to the mass. So as you can see in the diagram, when the mass is larger, so it needs a lot of force and larger force to move the object. Okay, for the last one, for the Newton law of motion, is the Newton third law. Okay, definition. For every action, there is an equal force but in opposite direction. Okay, formula for the third law is F equal to negative. For the Newton third law, it involves action and reaction force. For example, that we can see is when we running or walking. Okay, when we run, the force push back and down our leg to the ground, and the reaction from that, the ground push forward and up of our leg. Okay, for the last example in the Newton third law is about the movement of the frog in the water. So, the pink arrow is action force and the green arrow is reaction force. So, when the frog push a leg backward, it will produce the reaction force in which make the frog to move forward.
Hi, okay, so for now I will proceed with the example question of Newton's law of motion. So for the first question is, a man is dragging a trunk up the loading ramp of a mover's truck. The ramp has a slope angle 20 degree and the man pulls upward with a force F whose direction makes an angle of 30 degree with the ramp. So first question is, how large a force F is necessary for the component Fx parallel to the ramp to be 60 Newton, and the second question is, how large will the component Fy perpendicular to the ramp then be? So I think that if we get this kind of question, it is better if we can draw the diagram so we can see clearly the force acting on the object. So now we first draw the diagram for the first question. We can use the formula Fx equal to F cos 30 degree, and we want to find for the F, so we make the F as a subject and we rewrite the formula again. Why we use cos 30 degree? Because the angle is stick to the x-axis. So for the Fx, we just substitute 60 Newton like from the from the equation, and we get and divide by cos 30 degree, and we get for the force is 69.28 Newton. For the second question, they want for the Fy, which is perpendicular to the ram. So we use the formula Fy equal to F sin 30 degree. Since we already get our force from the previous answer, so we just substitute for the question B, and we write 69.28 Newton times with sin 30 degree, and we get 34.64 Newton. Next example, a clock worker applies a constant horizontal force of 18 Newton to a block of ice on a smooth horizontal floor. The frictional force is negligible, which means that it doesn't have any frictional force. So the block starts from rest and move 11 meters in 5 seconds. First question is, what is the mass of the block of ice? And the second question is, if the worker stop pushing at the end of 5 seconds, how far does the block move in the next 5 seconds? So I think that if we it is better if we can take out all the information given from the equation. So I take out all the information that our T is 5 seconds, our F is 18 Newton, our initial velocity is 0 meter per second, and the changes of x is 11 meter. So for the first question, they want the mass of the block ice. So we can use the formula of F equal to ma, but since we don't have any acceleration, so we need to find the acceleration first by using the formula. The changes of x equal to initial velocity times t plus half a t squared. Since our initial velocity is 0 meter per second, so we just can cancel out, and we rewrite the formula and make acceleration as the subject. So we get 2 times the changes of x divided by t squared. So we just substitute the value, and we get the acceleration is 0.88 meter per second squared. So since we already get the acceleration, so we just can direct substitute for the F equal to ma, and we can get the mass, which is 90.9 kg. So for the second question is, they want how far does the block move. So first we need to find the velocity. So we use the formula of V equal to initial velocity plus AT. So we cancel out for the initial velocity, and we just substitute acceleration times t, like since we already get the acceleration, which is 0.88, and we times with the 5 seconds, so we get 4.4 meter per second. So for the next formula, we want to find how far, right? So we assume that the acceleration is 0. So we use the formula, the changes of x equal to initial velocity times t plus half a t squared. So since our acceleration now is 0, so we just can cancel out, and we just sub the value. The velocity is 4.440 meter per second times with 5 seconds, and we get 22 meter. So that's all. I will proceed with the next person.
So I will proceed with the next question from tutorial 1 for chapter 4. An electron leaves one end of a TV picture tube with a 0 initial speed and travel in a straight line to the accelerating grid, which is 1.80 cm away. If it reached the grid with a speed of 3.00 multiply 10 power 6 meter per second. If the accelerating force is constant, compute A, the acceleration, B, the time to reach the grid, C, the net force in Newton, and we can know the gravitational force on the electron. So the first one, we need to extract the information given from the question. From the question, we can get that the initial speed of the electron is 0 meter per second. So our U is 0 meter per second. Next, we can also get our distance traveled by electron, which is 1.80 cm. We need to convert this into meter, which is 1.80 multiply 10 power negative 2 meter, and this is equal to S. So we can also get the final speed of the electron, which is 3.00 multiply 10 power 6 meter per second, which is equal to V. So for the first question, we asked to find the acceleration. As the accelerating force is constant, we can use the equation of motion from chapter 2. So I choose to use V squared equal to U. squared plus 2as. As we have known value of v, u and s, we can substitute the value into the equation v squared equal to u squared plus 2s, and we can find the value of a. So the value of a is 2.5 multiply 10 power 14 meter per second. So for the question B, it asks the time to reach the grid. So we can use v equal to u plus at, as we have known the value of v, u and a. So we substitute the value of v, u and a into the equation, and we can get the value of t, which is 1.020 multiply 10 power negative 8 second. So for the last question, it asks the net force in Newton. So we can use the Newton's second law to calculate the force, which is F equal to ma. As the electron only travel in the x component, so we can conclude that the summation of Fx equal to ma. So the mass of electron is 9.11 multiply 10 power negative 31. So we can multiply the mass of electron with the acceleration we find in the equation A, and we can get the value of force, which is 2.2775 multiply 10 power negative 16 Newton. Next, I will proceed with the next question. A chair of mass 12 kg is sitting on the horizontal floor. The floor is not frictionless. From this sentence, we know that the mass of the chair is 12 kg and the floor has a friction force. You push on the chair with a force F equal to 40 Newton that is directed at an angle of 37 below the horizontal, and the chair slide along the floor. So from this sentence, we know that we put a force, which is the push force, equal to 40 Newton into the chair that directed at an angle of 37 below the horizontal. And the first question asks us to draw a clearly labeled free body diagram for the chair. Before we draw the free body diagram, I think it is easier for us to draw all the force exerted on the chair using information given from the equation. As you see in the slide, I draw something that look like chair. So, and for the push force that we put on the chair, it is 37 below horizontal. So we can divide this force into two components, which is the x component and y component. For the y component, it is Fy sin theta, and the theta is 37, while for the x component is Fx cos theta, and the theta is 37. So for the x component, also it contains kinetic friction force, and this kinetic friction force is opposite direction with the Fx cos theta. And for the y component, the normal force exerted on the chair is in the upward direction, while the weight and Fy sin theta, the exerted on the chair, is in the downward direction. So for the free body diagram, we can easily see that for the x component, we have in the right side is the Fx cos theta, while in the left side is Fk. And for the y component, in the upward direction, we have a normal force, and in the downward direction, we have weight and Fy sin theta. So for the question B, it asks us to use the diagram and Newton's law to calculate the normal force that the floor exerts on the chair. So from the free body diagram, we know that the normal force is in the y component, which is with the weight and Fy sin theta. And we can use Newton's first law, which is the summation of Fy equal to 0 to calculate it. So summation of Fy equal to 0 is equal to normal force N minus weight, which is W, minus Fy sin theta equal to 0. And we get the N is equal to weight plus Fy sin theta. Weight is equal to mg, and we know the mass of chair, which is 12 kg, and the g is gravitational acceleration, which is 9.81 meter per second squared. And we know the Fy equal to 40 Newton and theta is equal to 37. We can substitute all the value into the equation mg plus Fy sin theta, and we can get the value of N is equal to 141.6726 Newton.
Okay, next I will continue to the tutorial 4.54. The two blocks in figure P4.54 are connected by an heavy uniform rope with a mass of 4 kg and upward force of 200 Newton is applied as shown. Question A. Draw three free body diagram, one for the 6 kg block, one for the 4 kg block, and other one for the 5 kg block. For each force, indicate what body exerts that force. For the first figure, which is upper block, F is an upward force exerted by some external to the system agency. W is the downward weight of the upper block exerted by the earth, and TRU is the downward pulling force exerted by the rock. Referring to the figure 2, which is the rock, TUR is the upward pulling force exerted by the upper block, WR is downward weight of the rock, and TLR is the downward pulling force exerted by the lower block. Finally, the last one is lower block. TRL is the upward pulling force exerted by the rock, and WL is the downward weight of the lower block. According to the Newton's third law, we have TRU equal to TUR and TLR equal to TRL. B. What is the acceleration of the system? First, we denote the masses of the upper block, the heavy rock, and the lower block by MU, MR, and ML, respectively, and let the acceleration of the system be AY. Application of Newton's second law to the upper block give F minus W minus TRU equal to MU AY. Second, application of Newton's second law to the heavy rock give TUR minus WR minus TLR equal to MR AY. And application of Newton's second law to the lower block yields TRL minus WL equal to ML AY. Then we adding all the equations 1, 2, and 3, and we obtain F minus WU minus WR minus WL equal to MU plus MR plus ML times by AY. We know that W equal to mg, and we also know that the value of the masses and the force F. So solving AY and substituting the known values, we find that AY equal to F minus MU plus MR plus ML times by G divided by MU plus MR plus ML. And we substitute all the known values. We get 200 newtons minus 6 kg plus 4 kg plus 5 kg times by 9.8 meter per second square divided by 6 kg plus 4 kg plus 5 kg. We obtain the acceleration, which is 3.53 meter per second square. C. What is the tension of the top of the heavy rock? To answer the question, we substituting the result for AY, which is the acceleration of the system, into equations 1, give the tension TRU at the top of the rocks. We can get TRU equal to F minus WU minus WAY equal to F minus MU times by G plus AY. We can, when we substitute all the unknowns number, we can get 200 Newton minus 6 kg times by 9.8 meter per second square plus 3.53 meter per second square, and we can get the tension, which is 420 newtons. The last one is D. What is the tension of the midpoint rock? Okay, in the figure, rock shows that the free body diagram for the upper half of the heavy rock. Since the rock is uniform, the center of mass of its upper half is located at the middle of the upper half of weight, exactly half of the whole rock's weight. For example, the mass of the upper half of rock is mR over 2, as indicated in figure rock. Applying Newton's second law to the upper half of the rock give TUR minus WR over 2 minus T half equal to MR over 2 AY, where T half is the tension at the midpoint of the rock. It's exerted by the lower rock half of the rock, and WR equal to MRG. For solving the T half, and substituting the nonce value of mr, ay, and tur, which is equal to PRU SAM. Okay, we can find that T half equal to 2UR minus MR over 2 times by G plus AY equal to 120 newtons minus 4 kg divided by 2 times by 9.8 meter per second square plus 3.53 meter per second square. We get the tension at the top of the heavy rock, which is 93.2 newtons. That's all from us. Thank you.